In this video, I will discuss rationalizing numerators and denominators. Many of you know from Geometry and Algebra 2 that we generally do not like to leave radicals in the denominator of numeric expressions. And so what we do is we rationalize the denominator. We're going to begin here with a familiar example. Let's say that we were asked to rationalize 2 divided by the square root of 5. In order to work with an expression, we know that we write the original expression down, we leave it alone, we put an equals, and we move from left to right. And it is only in the first step here that we're going to actually show any changes or manipulations. In order to rationalize the denominator, to get rid of that radical, we're going to multiply by a special form of 1, just like we did with complex fractions. In this case, however, the special form of 1 we want to use is the square root of 5 divided by the square root of 5. In the numerator, that's going to give us 2 times the square root of 5, and in the denominator, that's going to give us the square root of 25, which we know simplifies to just a 5. And voila, we have gotten rid of the radical that was in the denominator. Most of the time, of course, we also skip this in-between step here. We know that the square root of 5 times the square root of 5 is equal to 5. This whole entire process was based upon this idea that we've seen before about multiplying by a special form of 1. However, the special form of 1 that we use is very dependent upon what kind of expression we have. So, for example, if I had had 2 divided by the cube root of 5, and I had tried to do a very similar process of multiplying by a special form of 1 using the cube root of 5 divided by the cube root of 5, you're going to see that that actually doesn't work for us here. Because in the numerator, I'm going to get 2 cube root of 5, and in the denominator, I'm going to get the cube root of 25. Well, 25 is not a perfect cube, and therefore the cube root of 25 doesn't simplify. I still have a radical left in the denominator. In this case, because we're working with a cube root, the special form of 1 that we want to use is actually the cube root of 25, which is the square of 5, divided by the cube root of 25. So now in the numerator, we get 2 cube root of 25. In the denominator, we get the cube root of 125. 125 is a perfect cube, and therefore that cube root simplifies, and we get 2 cube root of 25 divided by 5. So my point is that right here, the special form of 1 that you use depends a lot on what kind of expression you have. We're going to focus for the rest of this video just on having a square root and working with square roots. And so it's a pretty simple special form of 1 that you would use in this case. Our next example is a little more complicated. In this case, we actually have 2 radicals in the denominator, and they're separated by addition, so that is called a binomial. As before, we will begin by writing the original expression, leaving it alone, putting an equals, and working to the right. So it is here before we are actually able to start manipulating the expression. We're going to multiply by a special form of 1, and you might think that that special form of 1 is the square root of 3 plus the square root of 7 divided by the square root of 3 plus the square root of 7. However, if we think about the algebra that is going on here, what you have in that denominator is a binomial that looks like the form a plus b. So you're actually trying to multiply a plus b times a plus b. From algebra, we know that that would actually give us a squared plus 2ab plus b squared. We do not just square each term, there is that middle term. So in this case, the a is representing the square root of 3, and the b is representing the square root of 7, so we would end up with a middle term that's actually 2 times the square root of 3 times the square root of 7, and that wouldn't actually get rid of any of the radicals. So this is not the special form of 1 that we want to use in this case. Instead, let's remember another special product from algebra, and that is that if we take a plus b and multiply it by a minus b, we actually get a squared minus b squared. And this is very helpful because if a represents the square root of 3 and b represents the square root of 7, then a squared, the square of the square root of 3, is just a 3. and b squared is just a 7. And look, we'll have gotten rid of the radicals there. Now, a minus b in this case is something called the conjugate. And in fact, those are conjugates of each other, so it's also true that a plus b is the conjugate of a minus b. And that's what we're actually going to use in our special form of 1. So to rationalize a denominator that has a binomial with 2 square roots in it, the special form of 1 we're going to use, in this case for example, is the square root of 3 minus the square root of 7 divided by the square root of 3 minus the square root of 7. So in the numerator, we get 6 times the quantity, square root of 3 minus square root of 7. And in the denominator, like we saw here, we're going to get a squared, which is just 3, minus b squared, which is just 7. And there you go. We have gotten rid of the radicals that are in the denominator. This is based on using conjugates. This also only works with square roots because of what we're doing here of getting a square on there. So again, this is not the kind of thing that would work with cube roots. But continuing with our expression here, there's some simplifying we can do. So we get 6 times the square root of 3 minus the square root of 7 divided by negative 4. And we can actually cancel a common factor of 2 from the numerator and denominator. We can also take that negative and apply it to the numerator. We can move it up there. So we get negative 3 times the quantity, square root of 3, minus the square root of 7, all divided by 2. And you might think that you're finished at this point, and you've simplified things as much as you can. But I want to remind you of something else that we can show with some algebra here. And that is that the opposite of subtraction, so the opposite of the quantity a minus b, gives us the opposite of a plus b, which can be written more simply as b minus a. In other words, to take the opposite of subtraction, all you do is turn around the subtraction. The opposite of a minus b is b minus a. So we're going to use that to our advantage here to do just a little more simplifying on our expression. We're going to take this negative right here and apply it to this subtraction by simply turning the subtraction around. That then gives us 3 times the quantity square root of 7 minus the square root of 3, all divided by 2. And that's actually the preferred simplified form here, because instead of 2 negative signs, we only have 1. Math is about being concise. And now we have rationalized and simplified this expression. There are no more radicals in the denominator. So I want to point out that there is actually nothing mathematically incorrect about having a radical in the denominator. It's just that as a mathematical community, we've gotten together and agreed that we're not going to leave radicals in the denominator. But that's for numeric expressions. It actually turns out that for algebraic expressions, sometimes we do like to move the radicals from the numerator and put them down into the denominator. So one process that we'd like to learn is how to rationalize the numerator of an algebraic expression. So here's our final example. We want to show that the square root of x minus the square root of x minus 3 all divided by 3 is equal to the expression 1 divided by the square root of x plus the square root of x minus 3. When you are asked to show that something is true, that an equation is true, you cannot work with both sides of it, for example, multiplying both sides by something, because that would already be assuming that it's a true equation. The way that we show that an equation is true is we begin by working with one side of the equation as an expression and manipulating, moving left to right, top to bottom, manipulating it until we actually end up with the other side. So I'm going to begin here with the square root of x minus the square root of x minus 3 all divided by 3, and I'm going to rationalize the numerator. Notice we have radicals in the numerator this time. Because those are square roots and it's a binomial, we saw in the last example that the way to rationalize that is to multiply by a special form of 1 using the conjugate. So I'm going to multiply by the square root of x plus the square root of x minus 3. Notice that the sign I'm changing is the one right here. I'm making that a plus because here was the subtraction. This sign I'm not changing. That's underneath the radical, and that has nothing to do with the binomial itself. So now multiplying by a special form of 1 using the conjugate. In the numerator we see that we've got that a minus b times a plus b form that we had talked about before, and therefore what we get is a squared, in this case that's just x, minus b squared. Well, b squared is the quantity x minus 3, so I need to use parentheses to make sure that I'm going to distribute that subtraction correctly. In the denominator, we simply have 3 times the quantity square root of x plus square root of x minus 3. And as we saw with complex fractions, we're not going to actually multiply that out because there may be some simplifying that we can do later if we leave it factored like that. Continuing, in the numerator, we get x minus x plus 3, all divided by 3 times the square root of x plus the square root of x minus 3, or we simply get 3 in the numerator, and that's divided by 3 times the square root of x plus the square root of x minus 3. And looky there, we've got a 3 that's a common factor in the numerator and denominator. We can cancel it, and we get 1 divided by the square root of x plus the square root of x minus 3, which is exactly what we were asked to show is true. So for algebraic expressions, sometimes we like to rationalize the numerator, but it's still that same idea that when you have square roots and a binomial, you multiply by a special form of 1 using the conjugate.